And good evening, everyone. Today, we welcome Professor Ryo Yoshida to give us the final talk of our geometric data analysis seminar series. And today, his topic is machine learning for material discovery. And if you have any questions, please feel free to comment in the chat. And later, after the talk, Professor Yoshida will answer your questions. And also, if after Professor Yoshida's talk, just stay a while. And I think Kate from JGI Bristol will say a few words as concluding remarks. Thank you very much for joining in. And without further ado, let's welcome Professor Yoshida give us his talk. Please.
Yes, thank you for introduction, and also I'd like to express my great thanks to provide this wonderful occasion to especially to interact with the people from the UK. So today I'm going to talk about data science for the materials discovery, which is related to the research field called materials informatics. The materials informatics is an interdisciplinary research field of the data science and material science. Okay. So in general, the parameter space of the material science is very huge. For example, let's think about the chemical space of the small organic molecule. This chemical space of the small organic molecule is known to consist of the more than 10 to 60 potential candidates. Okay. The currently conventional database of the chemical compound recorded nearly 10 to 8. So that means that there is still quite huge spaces no one has gone before. And we want to discover the new material from the such huge universe of the material, especially they exhibit innovative property and structure and required in the application in the science and industry. The question here is, how do we address this big challenge by using data science as a key driver? Yeah. So, okay. Okay, to achieve this goal, and we here apply a basic workflow of data analysis that are commonly applied every day. Okay, the input variable here represent the design parameter, such as the structure of input material. And output is, for example, correspond to a property of our interest. Okay. Here, after input is denoted by S, the output is denoted by Y. Okay. So collecting the data on the S1, S and Y, and we derive the model, prediction model, which define the mathematical mapping from the S to Y. Given such a model, we then proceed with a backward prediction. Okay. So that explore the inverse mapping from the Y to S. Okay. The question here is how do we handle the we handle the complex and diverse object which is targeted by the material science into this workflow of data analysis. Okay. For example, how do we handle the input variable as an input variable and the molecule and crystal and complex microstructure of the composite material and so on. Furthermore, to solve the inverse problem, and we need a generator to produce such complex object. And how do we generate a molecule and crystal and microstructure and so on? So this is one of the main topics in this talk. Okay. So now we consider this is addressed by performing the Bayesian modeling and the inference. Okay, the forward model to make a prediction from the S to Y is given to the likelihood here, and further prior is placed here to narrow down the huge solution space into a promising subregion. With this formula of the Bayesian theorem, the forward prediction from the S to Y is inverted to the Y to S, then generating the material from this distribution, this posterior distribution, especially using the Monte Carlo technique in a way. And after specifying the target region of the property of the material is given here in the conditional. And we aims to identify the new material. Okay, so this is a workflow of the Bayesian analysis in the material data. So this is what we called Bayesian inverse material design. Well, this is implemented into our Python library called DNOPy. So with this platform, and we can perform the Bayesian analysis for the various kind of the material, so which will be demonstrated here after. Okay. And to see this, okay, I first show the simple example taken from our study. Okay. The target is a discovery of the new polymer that exhibit high thermal conductivity. Okay. And using the data from the Polyinfo, which is the world's largest database of polymer property, and we first derived a model to make a prediction from the S to Y that predict a set of target property, which is denoted by Y, from the chemical structure of the repeating unit of the polymer. Okay. So target property include thermal conductivity. This is a primary target to our study. And also the target include glass transition temperature and melting temperature and heat capacity and so on. And by solving this inverse problem, and we predict chemical structure exhibiting the high thermal conductivity. Then after that, the predicted polymer are synthesized and experimental validation is conducted. Okay, now let's see this. Okay, and in the forward prediction, the first things we need to do is a conversion of the input chemical structure into a feature vector, which is called descriptor. Okay. So one typical example is the use of the molecular fingerprint. Okay. So in this example, the input molecule, the chemical structure is translated into a vector of binary digit. Okay. So each element takes value 1 or 0 according to the presence of the chemical fragment, which are usually the 1,000 or more chemical fragments are prepared and constructed. Other than this, we can use, for example, the positive definite kernel for the molecular graph, or more recently, graph-based neural network has greatly contributed to address this task. Okay. Anyway, so once this is done, the task can be addressed by performing the conventional regression, collecting the data on the S and Y. We perform the regression or classification to obtain the prediction model. Okay. And such a model is given to the likelihood here, okay? And prior is set, okay? We can define the posterior. Okay? So conducting the Monte Carlo calculation, so we want to identify the set of virtual material with their property fall into the desired target region specified here, okay? The idea is very simple, okay? But the problem to be considered here is the choice of the prior distribution, okay? So our solution space is very, very huge. So we need to effectively remove the non-target solution in a way. For example, the generated molecular graph must satisfy the rule of chemistry, and we have to exclude the occurrence of chemically unrealistic bond, or generated molecule should satisfy or have a high chemical stability or high synthetic accessibility. In some cases, we focus on the specific types of the molecule required for the application in the science and industry. For example, we aim to generate drug-like molecule and liquid crystal polymer and so on. So that's okay. So to see this, okay, for example, we may focus on the design of the specific polymer, which is called epoxy resin. Okay. On the other hand, in application to the development of organic solar cell, the donor molecule of organic solar cell should have a highly planar structure so as to stack in the layered material as shown here, like this, okay? So making the such prior distribution, probability distribution or generator by hand might be time consuming. So therefore, we will take a machine learning approach to the automated design of the prior distribution or generator for the molecule. Okay. So generative model is a trained to mimic by using the any given training instance of the such existing material. So this is one of the key component in the materials informatics application. Okay. So to this end, we here use a language model as an example. Okay. So it's well known that any molecule can be represented by a string, okay, called the SMILES representation like this. So this is an example of the SMILES representation of the a molecule called vanillin like this, which can be represented into the SMILES string like this. Okay. So here, a ring structure is surrounded by the same digit, okay, 1 and 1. Inside of string represent ring structure here. And the bracket indicate the side chain with respect to the main chain of this compound. Okay. So then collecting the set of the SMILES string from the public database or existing molecule, and language model is a train, such as a classical n-gram or recurrent neural network to run the ordering and the pattern, the frequency of the token in the existing material molecule. Then such a trained model is given to the prior here, and substructure is fixed. And the prior suggests, okay, how do we generate remaining component structure so as to ensure the chemical reality or to have a specific feature of our target chemical. And then likelihood evaluate the closeness to the target region. Okay. So we generate a molecule from this posterior distribution, which is given to again the condition, and repeating this condition sampling many times, we aimed to generate to obtain the set of virtual compounds satisfying the target property. Okay. So this is an example of the application. Okay. So two target property here, glass transition temperature and melting temperature are shown on the horizontal and vertical axis. Okay. The orange denote our training data which are taken from the public database. Okay. The target region is denoted by the rectangle. Okay, higher temperature and higher melting temperature, higher glass transition temperature and melting temperature are our target. Okay, and starting from the 20 initial molecule, which are taken from the public database, and we repeat the sampling on the molecule from the conditional distribution. Okay, and the resulting property gradually get closer to the target region corresponding to the high glass transition temperature and melting temperature in this way, okay, where the no data are given, and created molecules are ensured to hold a chemical reality or a particular structural feature encoded into our prior, which is referred to as a liquid crystal likeliness. Okay. So to do this kind of the backward calculation for the various application, okay, generative model will be the key. Okay, and generative model that can move freely around large chemical space is required to obtain. Okay, and more recently, various kind of the deep generative model have been developed in the machine learning community. For example, LSTM or variation of the encoder and generative adversarial network were commonly applied for the generation of the chemical structure and crystal structure and the higher order structure of the polymer and the other molecular system and so on. So it's really interesting to me that such research is originating from the machine learning community. Okay. So in this study, we finally created 10,000 candidate of polymer as exhibiting the high thermal conductivity. And finally, 3 new polymers shown here are synthesized, and their experimental property for the thermal conductivity are validated by our experimentation. And also it was confirmed the synthesized polymers exhibit the solubility to an organic solvent and also show the glassy state and liquid crystallinity. Okay, and some of the synthesized molecule showed about 40% higher thermal conductivity than the conventional polymer. Okay, so this would be one of the first successful application of the machine learning based inverse design of polymer, and we reached a milestone. On the other hand, some big issues still remain unresolved. Okay, so this is the next topic. So one big issue considered here is, okay, so we need to overcome the hurdle of chemical synthesis. Okay, here I will briefly describe the machine learning technique on this task, which is called retrosynthesis. Okay, the concept of and the methodological foundation of the retrosynthesis analysis was first developed by the Professor Carlo in Harvard University, and he received the Nobel Prize in chemistry in 1990 on this historical achievement. And his first paper was published in 1969, and he proposed a rule-based artificial intelligence system for the designing the synthetic route to a any given target molecule. And after 50 years, okay, the latest technology of the machine learning are now overturning the process of the retrosynthesis. So I will show briefly. Okay, so first, the problem is formulated, okay? So design target is given by our computational algorithm. And we want to identify the route of chemical synthesis, reaching to this target by performing the multi-step synthetic reaction. Okay, this is a problem. Okay, so given the list of the commercially available compound, and we need to select initial compound and reactant and reagent or catalysis to promote this chemical reaction. Okay, this is a problem, and this is like a combinatorial problem. Usually the number of commercially available compound is of order 10 to 6. Okay, then the solution space is defined by their all possible combination of the commercially available compound. So quite huge space should be taken into account. Okay. So to solve this problem, and we first perform the forward prediction and backward prediction after that. In the forward problem, okay, so objective is to obtain the machine learning model that predict the product of the single step reaction. And a set of reactant and reagent were given as an input. Okay. Here we represent input and output variable based on the SMILES representation. Okay. The reactant and the reagent and product are all represented by the SMILES string. And in the middle of the reactant and reactant 2, they are separated by the period, and reagent are specified after the symbol of inequality. Okay. And also product is also represented by the SMILES string. Okay. Then the problem is to find the rule of conversion from the strings to strings. Okay. Therefore, the neural network for the machine translation task could be used to address this problem. Okay. Such as attention-based neural network, including the 6-to-6 and transformer. Okay. So by the recent study, such model trained on the million of reaction data taken from the public database can reach the tremendous performance on the forward prediction. For example, the transformer architecture exhibit about 90% accuracy in top 1 accuracy. In the top 5 accuracy, 95% of chemical structure in the test product can be perfectly predicted. Then, given such a model, okay, we can simulate forwardly the synthetic reaction. Okay. Here, for example, consider 2-step reaction as a template, and 2 reactant S1 and S2 are selected. By using our model, we can calculate the intermediate product X. And by selecting the reactant 3, okay, we can calculate the final product. Okay. Here, the target product is fixed to be a target. Then we explore all possible combination of the 3 unknown reactant S1, S2, and S3, so as to reach the target specified here by solving the backward prediction mode task. Okay. So this is a problem, and we conduct the this backward prediction task based on the Bayesian inference using the posterior. Posterior distribution is defined as follows, which is proportional to the joint distribution of the S and Y. And we model this as a Gaussian distribution like this. The temperature is here, and energy function measures the similarity between the desired target, synthetic target, and also the prediction made by our forward model. Okay. So this is a problem. Okay. And also, it should be noted that posterior distribution is a discrete measure which is defined over all possible combination of the purchasable compound that we used. Okay. So the number of potential candidates is of order 10 to 80 if we use the number of commercially available compound is 10 to 6. The solution space is defined by the all possible combination of 3 reactants. Okay. So this is a very big, serious problem. Okay. The exact computation of the posterior distribution is infeasible. Okay, so this is a defined over the all solution space denoted by T, and so we need an approximation to compute posterior distribution, and using the much smaller number of the reactant pair in an effective way. Okay. And to do this, so conventional heuristic approaches are not applicable, and we are thinking, so there are many potential candidates, okay, not yet discovered to reach the same target. And so we want to identify such diverse solution comprehensively. This is our challenge. And to achieve this goal, and we adapted a coarse-to-fine strategy into the sequential Monte Carlo method. So here I show only the basic idea. So details are shown in our paper. Okay. So we first sampled the so there are quite large number of the solution yet to be discovered. Okay, and we first sample some particle, and which clustered into here in the three cluster. Okay, and so so three cluster, and so we first okay, so they are clustered into a three cluster feature is color coded. Okay, in this way. And then their cluster level likelihood are evaluated by using the surrogate model that are trained on the before starting the calculation of the SMC. And then remove the unpromising cluster, and we calculate the likelihood of the surviving particle. Okay, then survived particle are removed from the candidate because our problem is a discrete, the random sampling from the discrete. Okay, okay, and then proceed with the next step. And looping this process many times, we identified a set of diverse synthetic root. So sorry, details are omitted here. Yeah. So here I just show the one example and the result taken from our paper. Okay, so our algorithm suggests in this application more than 6,000 candidate routes to reach the same synthetic target shown here. Okay, okay, so our algorithm suggests there exists such a diverse synthetic route by using which can be possible, feasible to synthesize using the currently given the commercial compound. And also they formed 98 different clusters according to the chemical structure involved in the reaction pathway. And also according to the evaluation made by our expert chemist, the 35 to 6% of the proposed synthetic reaction would be chemically valid and synthesizable. And such candidates are provided to a chemist, and they will make a final decision making for this purpose. And diversity of the candidate will be very important to enhance the creativity of the researcher in the organic synthesis. Okay. We are thinking, so this kind of the machine learning technology will be a groundbreaking technology in the next era of the organic chemistry. And in organic chemistry, the recent advance of the machine learning technology enabled us to automate the computational design of the chemical compound and also their synthetic route as well. The next challenge is to integrate such machine learning system into a robot to fully automate experimentation. Okay, so this is a challenge that has already started, and one so which some of our outstanding study arise from the For example, the University of Glasgow in UK, or Harvard University and MIT. Okay. So this will provide a really exciting opportunity to us. Okay. Okay. So now we will move on the next topic on the machine learning for the designing the manufacturing process for more complex composite material. Okay. So this diagram shows the flowchart corresponding to the process to microstructure and microstructure to property. Okay. So the choice of process parameter and composition, okay, control the microstructure of the material. Okay. This microstructure also controls the property or functionality of the resulting material. And the question is, how do we incorporate the data science technique in this workflow? Okay. Here, as an example, we treat the microstructure as an image of electron microscopy. For example, the SEM, scanning electron microscopy, which is called SEM. Okay. So material researcher routinely acquires such microscopic image every day. Okay. Then the prediction task from the structure to property can be formulated as a conventional problem of image recognition. And on the other hand, the task of the prediction from the process to microstructure can be treated as an image generation task. Okay. Okay, so now let's see a specific example taken from this study. Okay. So the input variable considered here is a 6-dimensional real-valued vector that consists of the 2 compositional parameters of the inorganic material and the 4 process parameters such as deposition temperature or deposition pressure and so on. Okay. This is a very important parameter for the sputtering of the thin filmed material. Okay. The output is a microscopic image of the microstructure material, and collecting the data on the input and output. So we here trained a deep generative model. The dataset that we use is originated from the 123 electron microscopic image and 2 augments dataset. So we generated randomly the 128 patch by using the random sampling. So this is our dataset. And okay. So to be specific, and here we use a conventional conditional GAN. Maybe so perhaps, so it no longer need to explain about GAN for the participant today's seminar. Okay, so here only the difference of the conditional GAN to a conventional GAN is to include the 6-dimensional conditional parameter into the input of the G generator and discriminator. Okay, so G is trained to fool the D, and D is trained not to be fooled by G. Okay, so looping this alternative learning scheme many times, the resulting G can be used to predict the prediction model of the microstructure image for any given conditional parameter corresponding to the process and composition. So this is used for the regression model. So this slide highlights the prediction ability of our model on the 6 different conditions from the A to G, which corresponding to the different conditional parameter. Okay. So predicted image is shown on the top panels, and the predicted image exhibit a good agreement to the real image taken from the microscopic experiment and corresponding to the different grain, size, and the topological feature. So even if we removed all similar image from the training set, our model exhibits a good agreement to the real data. So such a model is given, so we may perform backward prediction to search for the set of conditional parameters that achieve the specific pattern of the grain size and topological feature. So in order to improve the mechanical property of the material, and we want to make a crystal grain size smaller and more uniform, so our model can provide the answer to such question. Okay. So this kind of the machine learning can be considered as a regression technique for the multidimensional output in the material science. So there are many such potential applications yet to be explored. So in which the high dimensional output should be handled for the regression. In the study of the microstructure, in our case, the Y is given as a matrix to represent the grayscale image of the microscopic image. Or on the other hand, in the study of the optical material, we want to predict the light absorption spectrum of the like this, which is defined over the frequency for any given input molecule. Okay. In this case, the output variable is represented as a function. Okay. And also there let's think about the AlphaFold, okay, which is developed by DeepMind in order to make a prediction of the protein folding structure, which is a very popular model. And then deep neural network was used. The input is an amino acid sequence, which is a string, one-dimensional string types of input. And the output is a matrix called the contact matrix, which represents the distance of the atom to atom in the 3D structure of the protein holding, okay, and so on. So in such a case, the space of the output variable is very high dimensional, and making the direct application of the conventional regression approach unstable and infeasible, and due to the lack of identifiability in the learning objective. And to enhance the stability of the learning scheme, and the adversarial example are generated and added to our training data set, which play a role of the regularization. Okay. So now, and we will move to our next topics. Okay. So the ultimate goal of the material science is to realize the extrapolative prediction and extrapolative discovery. This is a very important goal to our science. However, the prediction made by any statistical model is interpolative in nature. So our interest is lying in the here is laid on the question. Okay, how do we overcome the limitation of the interpolative prediction made by data science? Okay, so to see this, and let's consider an example taken from the study of the organic solar cell. Okay, so this figure shows the distribution of donor molecule of the organic solar cell device. Okay, so vertical and horizontal axis denote homology gap and power conversion efficiency. Okay, in 2012, okay, the best performing donor molecule achieved the 11% in the power conversion efficiency. But here, getting back to 2009, okay, the distribution of the donor molecule was as shown in here. Yeah. So we are now interested in how do we identify the best material in 2012 only by using only the data available until the 2009 indicated by blue. Okay. In general, it's a difficult, quite difficult. This is a very difficult problem because any statistical model lacks the ability of the prediction in the region. So no data available. Okay. So I'd like to skip. And so this slide demonstrates the limitation of the interpolative prediction made by data science method. So two target property, the homology gap and the power conversion efficiency are now converted to the HOMO and LUMO. Okay, using the HOMO and LUMO are shown on the horizontal and the vertical axis. Okay, so this has been made by using the theoretical model from the physics. And this conversion, and we can validate the predict value of the machine learning model by using the first principle calculation. That is a validation experiment made by the computer experiment. And the blue denotes the data in 2009, and red denote the virtual molecule created by our Bayesian method. And the target region is represented by the rectangle, which corresponds to the best performing material in 2012. And note that here, all the properties shown here are validated by using the first principle calculation. Okay, so as you can see from this figure, the created molecule shown by red get stuck around region, reaching to the ultra extrapolative target region. Okay, so our model has lacks the ability of the prediction in that region. So we failed to reach the target region. So this is a limitation of the conventional data science approach. Okay. So to overcome this limitation, and we need to integrate a data production system or fully automated experimentation system into the machine learning system framework based on especially the statistical method for the adaptive design of experiments. So this diagram shows our system called Spatial. Okay. So Bayesian method, our Bayesian method is used to produce the large amount of the hypothetical and virtual molecule. Each subset is selected according to the module of the experimental design in a way. In this system, we applied the Bayesian optimization method. Okay, and the selected molecule is given to the module of the experimentation. And in this case, so using the first principle calculation, we measure the target property of design point to be selected, and the feature given to the as an additional training instance, and so features are used to enhance the extrapolative ability of our model. And this process is repeated many times, such as more than 1 month and 2 months. And our algorithm, Spatial, will gradually acquire the extrapolative prediction ability. So technical details are omitted here because the time is limited. And so if you have a question, so I will give an answer to the technical aspect of our scheme. And so I just show the result here. Okay, so how let's see the results. Okay, so we started from the existing material data, and starting from here, and created the molecule get closer to the target region by the conduction of the spatial algorithm. And finally, around step 6, and the spatial maybe successfully reach the target region in this way, and keep this kind of computation in a very long time, and we can identify the large number of promising molecules. So this is a really exciting opportunity to us. Okay. So here, so the one of the so this is a important question. So here we encounter the big question. Okay. So this slide shows the TSNE prediction of the molecule created by our algorithm, and also the recorded in our database. So which are made on the knowledge on the human intelligence. Okay, this is the TSNE projection of the old molecule. The orange denote our molecule and blue denote the molecule recorded in the database. So what I want to show here is there is a large gap between the material discovered by the human knowledge and created from the virtual laboratory based on the machine intelligence. So so that means the spatial could identify the large number of novel molecules yet to be discovered. On the other hand, our method overlooked a large number of already discovered molecules. So we are always every day thinking about why such a large gap occurs between the human and machine intelligence. Fortunately, at this moment, we have no clear answer to this, so we are still thinking about this mystery. Okay. Okay. Sorry. Doesn't work. Okay. Finally, so in terms of the extrapolative prediction, so I'd like to briefly give a remarks on the great potential of the transfer learning. Okay, so most of the data in our area are very small and much smaller than the data in the other application field of data science. And here we are thinking the transfer learning or domain adaptation become the key driver to overcome this big hurdle. Okay. So this is an example taken from our study. Okay. So the target is a discovery of the inorganic crystal with a high thermal conductivity. However, when we started this project, we only have a 45 data on the thermal conductivity. So we decided to use an alternative target property, which is called scattering phase space. Hereafter, we call it SPS. Okay. We collected the data on the SPS, 320 sample for the SPS, the which are used for the source data set in the transfer learning. And as shown in this figure, okay, these two properties exhibit a weak correlation. The SPS and thermal conductivity are shown on the horizontal and vertical axis. Okay. Very weak negative correlation are present. And to overcome the hurdle of the limited amount of data, and if here we apply the commonly applied transfer learning using the neural network, and using the 320 data on the SPS, we trained a 3-layered and fully connected neural network, which transfer to the target task in making the prediction of the thermal conductivity. And to be specific, the subnetwork of the pre-trained model other than top layer is copied, okay, to the target task. And the parameter in the linear model in the top layer was estimated by using the 45 sample of the thermal conductivity. This is what we did, and we do nothing special other than this. Okay. I only use the conventional workflow of the transfer learning. And this shows the predicted value of the pre-trained model on the SPS, and the prediction and observation are shown on the horizontal and vertical axis. This was transferred to the model on the thermal conductivity. So this shows the result of the tenfold cross-validation that were looped within the 45 data point. And as you can see from this figure, they exhibit a good agreement in this way. And finally, so using this model, we performed the screening over the 70,000 material taken from the public database, which include the real and virtual compound. Okay. And so we finally discovered 40 crystals. Okay. Some of them exhibit very high thermal conductivity as reaching more than 3,000 watt per meter Kelvin. Okay. So this is one of the successful applications. And here, I'd like to describe the great potential of the transfer learning, okay, in the terms of the extrapolative ability. So this histogram shows the distribution of the 40 crystals that we discovered, okay, as indicated by green. And some of them reached more than 3,000 watt per meter Kelvin in the thermal conductivity. On the other hand, our training data, which is denoted by yellow, are distributed in a much lower region. Okay, so our model is trained on this data set and to make a prediction of this material. Okay, so this slide shows the prediction result of the 14 crystals that we identified with respect to the result of experimental validation. Okay, as you can see, and except for the few material, and our predicted value of our transferred model exhibit a good agreement to the experimental observation, even in such extrapolative region of target. And the blue dot denote the result of the prediction made by the model, directly trained on the 45 data point as indicated by yellow. Okay. As you can see, the predicted value of the such directly trained model saturate around the upper region of the training data. This is a typical result of the direct machine learning. The transfer learning can be have made a great contribution to overcome the limitation of the interpolative prediction made by the conventional scheme of the machine learning. And inspired by this great success of the transfer learning, and we decided to use the transfer learning in a systematic way in this research field, and collecting the massive amount of data from the public domain. We constructed massive amount of the pre-trained model for the various property and various material, including the small organic molecule and polymer and the inorganic crystal and their composite and so on. And so this model library is implemented into our software and provided as a database. Okay. Maybe so the time is approaching, so I should skip some of the results. Okay. So I should conclude this talk now. Okay. Okay, so finally, I'd like to make a position talk a little bit. So I'd like to introduce the research center in the ISN. In 2017, our institute launched a research center called Data Science Center for Creative Design and Manufacturing. So the name of center is a little bit long. I want to make it shorter. That the mission of this center is to show the real impact of data science in the field of manufacturing, one of the target is related on the material science. And we are conducting the many study, really many study that cover the broad range of the advanced material, such as polymer and polymer composite or thin filmed layered material and optical device and so on. Okay. So many professionals, scientists and engineers in various research fields are coming together here and from the science and industry. So after beating the COVID-19, and you may have a chance to visit ISM, I hope that you will have an opportunity to interact with our team in ISM. And most important things to be addressed now is to overcome the corona. Thanks a lot for your kind attention. My talk is now finished. Okay, thank you.
Thank you very much, Professor Yoshida, and for very inspiring and very interesting talk. Okay, so when Wang asked that, thanks, Professor, can the presentation slides be shared? I'm wondering if you can share the slides with us later?
Yeah, yeah, sure.
Okay, great. So there is another question that was sent by email. So Michael Wisnom asked the following question. That is, some simulation results were shown with high TG and melting temperature. Have these been successfully synthesized?
Okay. So in this study, yeah, we consider a synthetic route to the design target by hand based on the expert knowledge. Okay. So I don't know the experimental detail about how do we synthesize the, yeah. But so our paper provided the experimental detail of the synthesization of the three new polymer. So is it okay to
Right, I think Michael is not here. If Michael is here, could you comment a bit more on this or not? Okay, I think Michael is not here.
Yeah, no, I'm here.
Oh, yes. Right. Yeah, please.
Oh, no, I just saw the simulation results, and you were showing some extraordinarily high predicted TG and melting temperature. I was very interested to know whether these any of these have been successfully synthesized, because it looked very, very interesting.
Mm-hmm. Yeah.
Okay, so I think, yeah. So Professor Yoshida, do you want to comment a bit more, or that's the answer to the question?
Yeah, maybe so. I'm missing the point of the question or comment. Sorry. I say again, so I couldn't hear that clearly.
Okay, Michael, could you say it again, please?
Well, you showed some experimental validation of the conductivity.
Yeah.
I was wondering whether you had also done that for the high TG and melting temperature results.
Yeah. Yeah. Primary target of our study was thermal conductivity, but so at the same time, in order to the ease of the processing, so we specify the specific target range of the glass transition temperature. Maybe so the target range of the glass transition temperature was around 200, 200 Celsius degree. Okay. This is a requirement from the further industrial application. Okay. Yeah. And also we have to, we consider several type, different target property, and we, yeah. So yeah, one of the important target is we want to discover the to generate liquid crystal polymer. Okay, so in order to achieve this goal, we use the machine learning model to make a prediction of the liquid crystal likeliness, which are evaluated from the chemical structure of the monomer. And then this is also used for the target, our forward prediction model. Okay.
Okay, so thank you very much for answering. Let's move on to the next question. So Vincent asks, given the massive design space, can you give some idea on the time and computational cost of some of these simulations?
Simulation means the first principle calculation or the, yeah. Yes, so the bottleneck of our algorithm, for example, maybe so the question is related on this algorithm. I don't know whether or not
if you are here, could you explain a bit more, or you're just asking a more generic question about the computational cost or time cost? So, okay, so probably Vincent is not here, but I think he's asking a very generic question.
Generic question, okay.
Right, so about this search space is so big, and how do you, for example, balance?
Yeah, so if you want to explore the entire chemical space, so it's, of course, it's infeasible. And in practical application, and so in order to reduce the search space in a way, we specify this focus region. For example, if we are interested in the organic solar cell material, then we specify the focus region. Okay, in this way, we can reduce, we narrow down the possible solution space into a promising target. Okay, so yeah, and also the computational cost of the our Bayesian algorithm is very trivial, not so critical. But so one of the most the bottleneck of the computation is come from the computer simulation based on the physics. Okay, for example, in this application, in this algorithm, which is called Spatial, which made the integration of the machine learning based backward calculation, and also the computer simulation conducted based on the physical law that is called first principle calculation. So bottleneck of the computation time comes from the simulation module here. Okay. So due to this bottleneck, so yeah, for example, I showed this result. So we performed this algorithm only the 10 step. Okay. So to my understanding, so computation time for the 10-step calculation of our algorithm takes 2 weeks. 2 weeks. Yeah. So that is yeah, difficulty of the computation in the current system. Okay.
So I think Vincent just commented a bit. So I was referring to the training and then the finding of new solutions. For instance, when you are trying to get to a specific region, let's say in the TG and melting temperature, you showed how the various generations evolve. I was interested in how long do these generations take to generate and compute?
Yeah. So yeah, that in that generation, the computation time is a very trivial. And for example, we conducted several hundred steps for the successive modification of the chemical structure. So computation time was about 1 hour or 2 hours. By using the conventional workstation. Okay.
Okay. So I have a quick question regarding to generative adversarial network you were talking about. So in GAN, there is a common issue, that is the performance of GAN is really difficult to evaluate. You've mentioned that you use the GAN to generate some microscopic pictures. Yes, this slide. Could you briefly comment on how these performance were evaluated? And do you have a ground truth or measurements, error measurement for somehow to evaluate the performance of GAN?
Yeah, so this is just a preliminary result, and we are still evaluating the performance of the generative model from the conditional GAN. And so what I did at this moment is just to evaluate the similarity of the image generated from our model and the observation. And also, we have to consider more, investigate how more concretely, more systematically evaluate the performance of GAN. And also in the terms of the application in material science, so we have to investigate extrapolative ability of the prediction model. This is the prime ultimate goal of our study. And unfortunately, the conventional approach of the generative adversarial model network is very interpolative. So we are thinking how to overcome the limitation. Maybe so one of the promising solution is to incorporate the theory from the physics, which should be combined into a machine learning in a way. But so at this moment, I have no clear answer to this.
That's very impressive. Thank you very much. I think we have reached almost the end of today's talk. Thank you again for Professor Yoshida. And I think Kate from JGI Institute have a few words to say before we finish this session. And Kate, could you please? Yes.
Thank you, Song. Great to see you. Great talk, Ro. Thank you very much. So it falls to me really just to wrap up this fantastic seminar series that we've had. As many of you know, I've just put a link in the chat there. The partnership between Jean Golding Institute in Bristol and the Institute of Statistical Mathematics in Tokyo is a really kind of valued partnership by us all. This was initially intended to be a face-to-face workshop meeting. Obviously, life got in the way, but I think we should all agree that it's been an enormous success getting together in this way over the past 5 weeks. We've had some great talks. We've had a huge participation, probably greater than we would have done if we'd been face-to-face. Lily behind the scenes has been counting up participants, and we've got to over 100 over the course of the talks. We've had really wide-ranging talks. I've noticed from the names that I recognize in the participant list that we've had participation from across faculties within the University of Bristol. I suspect that's true on the Tokyo side as well. So we've had these series of talks have had really great reach, and it's wonderful to see. So first of all, some thanks. Thank you to Kenji Fukumitsu and for Song Liu, who together we three kind of organized the partnership. Thank you to Patrick as well, Ruben Donacci, for his support, to Patty Holly and Lily Rice from the Gene Golding Institute, who have worked so hard to support the events and all the behind the scenes tech that we maybe all take for granted, and to all our fantastic speakers over the past 5 weeks, without whom we wouldn't have had a series at all. In answer to one of the questions, yes, all the speakers have agreed to allow their talks to be made available. They'll be on the JGI website, and we will send an email around to you when they are available. We will have a feedback form. It'd be great if we could send this to you all. We'll send it out tomorrow to get a feeling for how successful you thought the format was, if the platforms worked for you, if there are any tech issues, if there are other kinds of topic areas that you'd like us to cover in future series like this. Any of that information would be really, really useful to us. So please do fill that out. And a final note, the Gene Golding Institute every year has a seed corn funding call, which is to establish cross-disciplinary connections using data science and different applications to get research projects going or to support an interesting research project. We fund between 5 or 10 a year, depending on how large the bids are. The call for this year will be launched on the 12th of October on our website. We'll have an information event that you're all welcome to join on the 21st of October, and there'll be an application deadline on the 23rd of November. So if any of the talks that you have heard over the last few weeks have piqued your interest, or you'd like to make connections, that might be a mechanism to keep that going over the next few months. And Song, I guess this is true for you and Kenji as well. If any of our participants have ideas for how we might want to grow the partnership between our two institutes, we'd love to hear from you, and we will do our best to facilitate those dialogues and work with you to achieve that. So Kenji, I think you're there. Any last words you'd like to say? Oh, he's put something in the chat. You've got a video problem, shame. I'd like to thank all the speakers.
Sorry, I have.
Hi, Kenji.
Hi, I have a video connection problem in the video connection today, so I can't show up. So, well, I just want to say thank you for all the speaker and the audience, and especially Bristol people who did a great work on organizing this online meeting series. So I thank them especially. Yeah, thank you.
Thank you, that's great. So it just remains for me to say thank you to everybody again. I hope you've enjoyed these talks as much as we have. Watch this space. We'll have some more activities going on with ISM in the coming year. And if you're interested in starting something new as a collaboration between our two partnerships, look out for our CCOR funding call. Okay, thanks everybody very much.